Calculus is the mathematical study of change, in the same way that geometry is the study of shape and algebra is the study of operations and their application to solving equations. It has two major branches: differential calculus, concerning rates of change and slopes of curves, and integral calculus, concerning accumulation of quantities and the areas under and between curves. These two branches are related to each other by the fundamental theorem of calculus. Both branches make use of the fundamental notions of convergence of infinite sequences and infinite series to a well-defined limit. Generally considered to have been founded in the 17th century by Isaac Newton and Gottfried Leibniz, today calculus has widespread uses in science, engineering and economics, and can solve many problems that algebra alone cannot. Calculus is a part of modern mathematics education. A course in calculus is a gateway to other, more advanced courses in mathematics devoted to the study of functions and limits, broadly called mathematical analysis. Calculus has historically been called the calculus of infinitesimals or infinitesimal calculus. The word calculus comes from Latin calculus and refers to a small stone used for counting. More generally, calculus, plural calculi, refers to any method or system of calculation guided by the symbolic manipulation of expressions. Some examples of other well-known calculi are propositional calculus, calculus of variations, lambda calculus, and process calculus. History. Modern calculus was developed in 17th century Europe by Isaac Newton and Gottfried Wilhelm Leibniz, but elements of it have appeared in ancient Greece, China, medieval Europe, India, and the Middle East. Ancient. The ancient period introduced some of the ideas that led to integral calculus, but does not seem to have developed these ideas in a rigorous and systematic way. Calculations of volume and area, one goal of integral calculus, can be found in the Egyptian Moscow papyrus, c. 1820 BC, but the formulas are simple instructions, with no indication as to method, and some of them lack major components. From the age of Greek mathematics, Eudoxus, c. 408–355 BC, used the method of exhaustion, which foreshadows the concept of the limit, to calculate areas and volumes, while Archimedes, c. 287–212 BC, developed this idea further, inventing heuristics which resemble the methods of integral calculus. The method of exhaustion was later reinvented in China by Liu Hui in the 3rd century AD in order to find the area of a circle. In the 5th century AD, Zhu Shangzi established a method that would later be called Cavalari's principle to find the volume of a sphere. Medieval. Alexander the Great's invasion of northern India brought Greek trigonometry, using the chord, to India, where the sine, cosine, and tangent were conceived. Indian mathematicians gave a semi-rigorous method of differentiation of some trigonometric functions. In the Middle East, Alhazen derived a formula for the sum of fourth powers. He used the results to carry out what would now be called an integration, where the formulas for the sums of integral squares and fourth powers allowed him to calculate the volume of a paraboloid. In the 14th century, Indian mathematician Madhava of Sangamagrama and the Kerala school of astronomy and mathematics stated components of calculus such as the Taylor series and infinite series approximations. However, they were not able to combine many differing ideas under the two unifying themes of the derivative and the integral, show the connection between the two, and turn calculus into the great problem-solving tool we have today. Modern. The calculus was the first achievement of modern mathematics, and it is difficult to overestimate its importance. I think it defines more unequivocally than anything else the inception of modern mathematics, and the system of mathematical analysis, which is its logical development, still constitutes the greatest technical advance in exact thinking. John von Neumann. In Europe, the foundational work was a treatise due to Bonaventura Cavalieri, who argued that volumes and areas should be computed as the sums of the volumes and areas of infinitesimally thin cross-sections. The ideas were similar to Archimedes in the method, but this treatise was lost until the early part of the 20th century. Cavalieri's work was not well respected, since his methods could lead to erroneous results, and the infinitesimal quantities he introduced were disreputable at first. The formal study of calculus brought together Cavalieri's infinitesimals with the calculus of finite differences developed in Europe at around the same time. Pierre de Fermat, claiming that he borrowed from Diophantus, introduced the concept of inequality, which represented equality up to an infinitesimal error term. The combination was achieved by John Wallis, Isaac Barrow, and James Gregory, the latter two proving the second fundamental theorem of calculus around 1670. Isaac Newton developed the use of calculus in his laws of motion and gravitation. The product rule and chain rule, the notion of higher derivatives, Taylor series, and analytical functions were introduced by Isaac Newton in an idiosyncratic notation which he used to solve problems of mathematical physics. In his works, Newton rephrased his ideas to suit the mathematical idiom of the time, replacing calculations with infinitesimals by equivalent geometrical arguments which were considered beyond reproach. He used the methods of calculus to solve the problem of planetary motion, the shape of the surface of a rotating fluid, the oblateness of the Earth, the motion of a weight sliding on a cycloid, and many other problems discussed in his Principia Mathematica, 1687. In other work, he developed series expansions for functions, including fractional and irrational powers, and it was clear that he understood the principles of the Taylor series. He did not publish all these discoveries, and at this time infinitesimal methods were still considered disreputable. Gottfried Wilhelm Leibniz was the first to publish his results on the development of calculus. These ideas were arranged into a tricalculus of infinitesimals by Gottfried Wilhelm Leibniz, who was originally accused of plagiarism by Newton. He is now regarded as an independent inventor of and contributor to calculus. His contribution was to provide a clear set of rules for working with infinitesimal quantities, allowing the computation of second and higher derivatives, and providing the product rule and chain rule in their differential and integral forms. Unlike Newton, Leibniz paid a lot of attention to the formalism, often spending days determining appropriate symbols for concepts. Leibniz and Newton are usually both credited with the invention of calculus. Newton was the first to apply calculus to general physics, and Leibniz developed much of the notation used in calculus today. The basic insights that both Newton and Leibniz provided were the laws of differentiation and integration, second and higher derivatives, and the notion of an approximating polynomial series. By Newton's time, the fundamental theorem of calculus was known. When Newton and Leibniz first published their results, there was great controversy over which mathematician, and therefore which country, deserved credit. Newton derived his results first, later to be published in his method of fluxions, but Leibniz published his Nova Methodes Pro Maximus et Minimus first. Newton claimed Leibniz stole ideas from his unpublished notes, which Newton had shared with a few members of the Royal Society. This controversy divided English-speaking mathematicians from continental mathematicians for many years, to the detriment of English mathematics. A careful examination of the papers of Leibniz and Newton shows that they arrived at their results independently, with Leibniz starting first with integration and Newton with differentiation. Today, both Newton and Leibniz are given credit for developing calculus independently. It is Leibniz, however, who gave the new discipline its name. Newton called his calculus the science of fluxions. Since the time of Leibniz and Newton, many mathematicians have contributed to the continuing development of calculus. One of the first and most complete works on finite and infinitesimal analysis was written in 1748 by Maria Gaetana Anasi. Maria Gaetana Anasi. Foundations. In calculus, foundations refers to the rigorous development of a subject from precise axioms and definitions. In early calculus, the use of infinitesimal quantities was thought unrigorous, and was fiercely criticized by a number of authors, most notably Michel Rolle and Bishop Berkeley. Berkeley famously described infinitesimals as the ghosts of departed quantities in his book The Analyst, in 1734. Working out a rigorous foundation for calculus occupied mathematicians for much of the century following Newton and Leibniz, and is still to some extent an active area of research today. Several mathematicians, including Maclaurin, tried to prove the soundness of using infinitesimals, but it would not be until 150 years later when, due to the work of Cauchy and Weierstrass, a way was finally found to avoid mere notions of infinitely small quantities. The foundations of differential and integral calculus had been laid. In Cauchy's writing, See Cowers Analyze, we find a broad range of foundational approaches, including a definition of continuity in terms of infinitesimals, and a somewhat imprecise prototype of an definition of limit in the definition of differentiation. In his work, Weierstrass formalized the concept of limit and eliminated infinitesimals. Following the work of Weierstrass, it eventually became common to base calculus on limits instead of infinitesimal quantities, though the subject is still occasionally called infinitesimal calculus. Bernhard Riemann used these ideas to give a precise definition of the integral. It was also during this period that the ideas of calculus were generalized to Euclidean space and the complex plane. In modern mathematics, the foundations of calculus are included in the field of real analysis, which contains full definitions and proofs of the theorems of calculus. The reach of calculus has also been greatly extended. Henry Lebesgue invented measure theory and used it to define integrals of all but the most pathological functions. Lawrence Schwartz introduced distributions, which can be used to take the derivative of any function whatsoever. Limits are not the only rigorous approach to the foundation of calculus. Another way is to use Abraham Robinson's non-standard analysis. Robinson's approach, developed in the 1960s, uses technical machinery from mathematical logic to augment the real number system with infinitesimal and infinite numbers, as in the original Newton-Leibniz conception. The resulting numbers are called hyperreal numbers, and they can be used to give Leibniz-like development of the usual rules of calculus. Significance. While many of the ideas of calculus had been developed earlier in Egypt, Greece, China, India, Iraq, Persia, and Japan, their use of calculus began in Europe during the 17th century, when Isaac Newton and Gottfried Wilhelm Leibniz built on the work of earlier mathematicians to introduce its basic principles. The development of calculus was built on earlier concepts of instantaneous motion and area underneath curves. Applications of differential calculus include computations involving velocity and acceleration, the slope of a curve, and optimization. Applications of integral calculus include computations involving area, volume, arc length, center of mass, work, and pressure. More advanced applications include power series and Fourier series. Calculus is also used to gain a more precise understanding of the nature of space, time, and motion. For centuries, mathematicians and philosophers wrestled with paradoxes involving division by zero or sums of infinitely many numbers. These questions arise in the study of motion and area. The ancient Greek philosopher Zeno of Elea gave several famous examples of such paradoxes. Calculus provides tools, especially the limit and the infinite series, which resolve the paradoxes. Principles. Limits and infinitesimals. Calculus is usually developed by working with very small quantities. Historically, the first method of doing so was by infinitesimals. These are objects which can be treated like numbers, but which are, in some sense, infinitely small. An infinitesimal number dx could be greater than 0, but less than any number in the sequence 1, 1/2, 1/3, and less than any positive real number. Any integer multiple of an infinitesimal is still infinitely small, i.e., infinitesimals do not satisfy the Archimedean property. From this point of view, calculus is a collection of techniques for manipulating infinitesimals. This approach fell out of favor in the 19th century because it was difficult to make the notion of an infinitesimal precise. However, the concept was revived in the 20th century with the introduction of non-standard analysis and smooth infinitesimal analysis, which provided solid foundations for the manipulation of infinitesimals. In the 19th century, infinitesimals were replaced by the epsilon delta approach to limits. Limits describe the value of a function at a certain input in terms of its values at nearby input. They capture small-scale behavior in the context of the real number system. In this treatment, calculus is a collection of techniques for manipulating certain limits. Infinitesimals get replaced by very small numbers, and the infinitely small behavior of the function is found by taking the limiting behavior for smaller and smaller numbers. Limits are the easiest way to provide rigorous foundations for calculus, and for this reason they are the standard approach. Differential calculus. Tangent line at x, f, x, the derivative f, x, of a curve at a point as the slope, rise over run, of the line tangent to that curve at that point. Differential calculus is the study of the definition, properties, and applications of the derivative of a function. The process of finding the derivative is called differentiation. Given a function and a point in the domain, the derivative at that point is a way of encoding the small-scale behavior of the function near that point. By finding the derivative of a function at every point in its domain, it is possible to produce a new function, called the derivative function, or just the derivative of the original function. In mathematical jargon, the derivative is a linear operator which inputs a function and outputs a second function. This is more abstract than many of the processes studied in elementary algebra, where functions usually input a number and output another number. For example, if the doubling function is given the input 3, then it outputs 6, and if the squaring function is given the input 3, then it outputs 9. The derivative, however, can take the squaring function as an input. This means that the derivative takes all the information of the squaring function such as that 2 is sent to 4, 3 is sent to 9, 4 is sent to 16, and so on, and uses this information to produce another function. The function it produces turns out to be the doubling function. The most common symbol for a derivative is an apostrophe, like mark called prime. Thus, the derivative of the function of f is f, pronounced f prime. For instance, if f x equals x2 is the squaring function, then f x equals 2x is its derivative, the doubling function. If the input of the function represents time, then the derivative represents change with respect to time. For example, if f is a function that takes a time as input and gives the position of a ball at that time as output, then the derivative of f is how the position is changing in time, that is, it is the velocity of the ball. If a function is linear, that is, if the graph of the function is a straight line, then the function can be written as y equals mx plus b, where x is the independent variable, y is the dependent variable, b is the y-intercept, and this gives an exact value for the slope of a straight line. If the graph of the function is not a straight line, however, then the change in y divided by the change in x varies. Derivatives give an exact meaning to the notion of change in output with respect to change in input. To be concrete, let f be a function, and fix a point in the domain of f. F is a point on the graph of the function. If h is a number close to 0, then a plus h is a number close to a. Therefore, a plus h, f a plus h, is close to f. The slope between these 2 points is. This expression is called a difference quotient. A line through 2 points on a curve is called a secant line, so m is the slope of the secant line between f and a plus h, f a plus h. The secant line is only an approximation to the behavior of the function at the point a. Because it does not account for what happens between a and a plus h, it is not possible to discover the behavior at a by setting h to 0, because this would require dividing by 0, which is impossible. The derivative is defined by taking the limit as h tends to 0, meaning that it considers the behavior of f for all small values of h, and extracts a consistent value for the case when h equals 0. Geometrically, the derivative is the slope of the tangent line to the graph of f at a. The tangent line is a limit of secant lines just as the derivative is a limit of difference quotients. For this reason, the derivative is sometimes called the slope of the function f. Here is a particular example, the derivative of the squaring function at the input 3. Let f x equals x to be the squaring function. The derivative f x of a curve at a point is the slope of the line tangent to that curve at that point. This slope is determined by considering the limiting value of the slopes of secant lines. Here the function involved, drawn in red, is f x equals x3x, the tangent line, in green, which passes through the point 3/2, 15/8, has a slope of 23/4. Note that the vertical and horizontal scales in this image are different. The slope of tangent line to the squaring function at the point 3, 9 is 6, that is to say, it is going up 6 times as fast as it is going to the right. The limit process just described can be performed for any point in the domain of the squaring function. This defines the derivative function of the squaring function, or just the derivative of the squaring function for short. A similar computation to the one above shows that the derivative of the squaring function is the doubling function. Leibniz notation. In an approach based on limits, the symbol dy/dx is to be interpreted not as the quotient of two numbers, but as a shorthand for the limit computed above. Leibniz, however, did intend it to represent the quotient of two infinitesimally small numbers, dy being the infinitesimally small change in y caused by an infinitesimally small change dx applied to x. We can also think of d/dx as a differentiation operator, which takes a function as an input and gives another function, the derivative, as the output. For example, in this usage, the dx in the denominator is read as with respect to x. Even when calculus is developed using limits rather than infinitesimals, it is common to manipulate symbols like dx and dy as if they were real numbers. Although it is possible to avoid such manipulations, they are sometimes notationally convenient in expressing operations such as the total derivative. Integral calculus. Integral calculus is the study of the definitions, properties, and applications of two related concepts: the indefinite integral and the definite integral. The process of finding the value of an integral is called integration. In technical language, integral calculus studies two related linear operators. The indefinite integral is the antiderivative, the inverse operation to the derivative. F is an indefinite integral of f, when f is a derivative of f. This use of lower and uppercase letters for a function, and its indefinite integral is common in calculus. The definite integral inputs a function and outputs a number, which gives the algebraic sum of areas between the graph of the input and the x-axis. The technical definition of the definite integral is the limit of the sum of areas of rectangles, called the Riemann sum. A motivating example is the distances traveled in a given time. If the speed is constant, only multiplication is needed, but if the speed changes, a more powerful method of finding the distance is necessary. One such method is to approximate the distance traveled by breaking up the time into many short intervals of time, then multiplying the time elapsed in each interval by one of the speeds in that interval, and then taking the sum, a Riemann sum, of the approximate distance traveled in each interval. The basic idea is that if only a short time elapses, then the speed will stay more or less the same. However, a Riemann sum only gives an approximation of the distance traveled. We must take the limit of all such Riemann sums to find the exact distance traveled. Constant velocity. Integration can be thought of as measuring the area under a curve defined by f, x, between 2 points, here A and B. When velocity is constant, the total distance traveled over the given time interval can be computed by multiplying velocity and time. For example, traveling a steady 50 mph for 3 hours results in a total distance of 150 miles. In the diagram on the left, when constant velocity and time are graphed, these two values form a rectangle with height equal to the velocity and width equal to the time elapsed. Therefore, the product of velocity and time also calculates the rectangular area under the constant velocity curve. This connection between the area under a curve and distance traveled can be extended to any irregularly shaped region exhibiting a fluctuating velocity over a given time period. If f(x) in the diagram on the right represents speed as it varies over time, The distance traveled between the times represented by A and B is the area of the shaded region S. To approximate that area, an intuitive method would be to divide up the distance between A and B into a number of equal segments, the length of each segment represented by the symbol x for each small segment. We can choose one value of the function f, x, call that value h, then the area of the rectangle with base x and height h gives the distance, time x multiplied by speed h, traveled in that segment. Associated with each segment is the average value of the function. Above it, f, x, equals h. The sum of all such rectangles gives an approximation of the area between the axis and the curve, which is an approximation of the total distance traveled. A smaller value for x will give more rectangles, and in most cases a better approximation, but for an exact answer we need to take a limit as x approaches 0. The symbol of integration is an elongated s. The s stands for sum. The definite integral is written as and is read the integral from a to b of f of x with respect to x. The Leibniz notation dx is intended to suggest dividing the area under the curve into an infinite number of rectangles so that their width x becomes the infinitesimally small dx in a formulation of the calculus based on limits. The notation is to be understood as an operator that takes a function as an input and gives a number, the area, as an output. The terminating differential, dx, is not a number and is not being multiplied by f, x, although, serving as a reminder of the x-limit definition, it can be treated as such in symbolic manipulations of the integral. Formally, the differential indicates the variable over which the function is integrated, and serves as a closing bracket for the integration operator. The indefinite integral, or antiderivative, is written. Functions differing by only a constant have the same derivative, and it can be shown that the antiderivative of a given function is actually a family of functions differing only by a constant. Since the derivative of the function y equals x2 plus c, where c is any constant, is y equals 2x, the antiderivative of the latter given by the unspecified constant c present in the indefinite integral, or antiderivative, is known as the constant of integration. Fundamental Theorem. Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus states that differentiation and integration are inverse operations. More precisely, it relates the values of antiderivatives to definite integrals. Because it is usually easier to compute an antiderivative than to apply the definition of a definite integral, the Fundamental Theorem of Calculus provides a practical way of computing definite integrals. It can also be interpreted as a precise statement of the fact that differentiation is the inverse of integration. The Fundamental Theorem of Calculus states, if a function f is continuous on the interval a, b, and if f is a function whose derivative is f on the interval a, b, then furthermore, for every x in the interval a, b. This realization, made by both Newton and Leibniz, who based their results on earlier work by Isaac Barrow, was key to the massive proliferation of analytic results after their work became known. The fundamental theorem provides an algebraic method of computing many definite integrals without performing limit processes, by finding formulas for antiderivatives. It is also a prototype solution of a differential equation. Differential equations relate an unknown function to its derivatives and are ubiquitous in the sciences. Applications. The logarithmic spiral of the Nautilus shell is a classical image used to depict the growth and change related to calculus. Calculus is used in every branch of the physical sciences, actuarial science, computer science, statistics, engineering, economics, business, medicine, demography, and in other fields wherever a problem can be mathematically modeled and an optimal solution is desired. It allows one to go from non-constant rates of change to the total change, or vice versa, and many times in studying a problem we know one and are trying to find the other. Physics makes particular use of calculus. All concepts in classical mechanics and electromagnetism are related through calculus. The mass of an object of known density, the moment of inertia of objects, as well as the total energy of an object within a conservative field can be found by the use of calculus. An example of the use of calculus in mechanics is Newton's second law of motion. Historically stated, it expressly uses the term rate of change, which refers to the derivative, saying the rate of change of momentum of a body is equal to the resultant force acting on the body, and is in the same direction. Commonly expressed today as force equals mass acceleration, it involves differential calculus because acceleration is the time derivative of velocity, or second time derivative of trajectory, or spatial position. Starting from knowing how an object is accelerating, we use calculus to derive its path. Maxwell's theory of electromagnetism and Einstein's theory of general relativity are also expressed in the language of differential calculus. Chemistry also uses calculus in determining reaction rates and radioactive decay. In biology, population dynamics starts with reproduction and death rates to model population changes. Calculus can be used in conjunction with other mathematical disciplines. For example, it can be used with linear algebra to find the best fit linear approximation for a set of points in a domain. Or it can be used in probability theory to determine the probability of a continuous random variable from an assumed density function. In analytic geometry, the study of graphs of functions, calculus is used to find high points and low points, maxima and minima, slope, concavity, and inflection points. Green's theorem, which gives the relationship between a line integral around a simple closed curve C and a double integral over the plane region D bounded by C, is applied in an instrument known as a planimeter, which is used to calculate the area of a flat surface on a drawing. For example, it can be used to calculate the amount of area taken up by an irregularly shaped flower bed or swimming pool when designing the layout of a piece of property. Discrete Green's theorem, which gives the relationship between a double integral of a function around a simple closed rectangular curve C and a linear combination of the antiderivatives values at corner points along the edge of the curve, allows fast calculation of sums of values in rectangular domains. For example, it can be used to efficiently calculate sums of rectangular domains in images in order to rapidly extract features and detect objects. See also the summed area table algorithm. In the realm of medicine, calculus can be used to find the optimal branching angle of a blood vessel so as to maximize flow. From the decay laws for a particular drug's elimination from the body, it is used to derive dosing laws. In nuclear medicine, it is used to build models of radiation transport and targeted tumor therapies. In economics, calculus allows for the determination of maximal profit by providing a way to easily calculate both marginal cost and marginal revenue. Calculus is also used to find approximate solutions to equations. In practice, it is the standard way to solve differential equations and root finding in most applications. Examples are methods such as Newton's method, fixed point iteration, and linear approximation. For instance, spacecraft use a variation of the Euler method to approximate curved courses within zero-gravity environments. Varieties. Over the years, many reformulations of calculus have been investigated for different purposes. Non-standard calculus. Imprecise calculations with infinitesimals were widely replaced with the rigorous definition of limits starting in the 1870s. Meanwhile, calculations with infinitesimals persisted and often led to correct results. This led Abraham Robinson to investigate if it were possible to develop a number system with infinitesimal quantities over which the theorems of calculus were still valid. In 1960, building upon the work of Edwin Hugh Tangerzio, he succeeded in developing non-standard analysis. The theory of non-standard analysis is rich enough to be applied in many branches of mathematics. As such, books and articles dedicated solely to the traditional theorems of calculus often go by the title Non-Standard Calculus. Smooth infinitesimal analysis. This is another reformulation of the calculus in terms of infinitesimals. Based on the ideas of F.W. Lauvier and employing the methods of category theory, it views all functions as being continuous and incapable of being expressed in terms of discrete entities. One aspect of this formulation is that the law of excluded middle does not hold in this formulation. Constructive analysis. Constructive mathematics is a branch of mathematics that insists that proofs of the existence of a number, function, or other mathematical object should give a construction of the object. As such, constructive mathematics also rejects the law of excluded middle. Reformulations of calculus in a constructive framework are generally part of the subject of constructive analysis.